Let me start with a scene you've probably lived through. It's a Friday night, you finally have time to plan a weekend trip. You start from TikTok, jump to Google Maps, open blogs, and finally compare prices on OTAs. After dozens of tabs, you still hesitate because the information is abundant but not organized around your intent. GoTogether was built for that exact moment. Our goal is simple: less searching, more experiencing. We'll help you quickly find places that match the vibe you want. Validate them using sentiment, not just star ratings, and then make it easier to agree as a group. I will walk through the problem, the research foundation, our implementation, and user feedback from a pilot study. Before the tech, let's quickly introduce the team behind it. Let us formalize the problem. Travel planning is increasingly a multi-source journey. Expedia research reports that, on average, travelers view 141 pages of travel content in the 45 days before booking, and many start without a specific destination in mind. This behavior is amplified for younger travelers who discover places through social media and creator content. This creates two practical pain points. First, information overload. Users must manually sync up inconsistent signal from maps, reviews, and short-form videos. And second, decision friction. Even after narrowing to a city, users still struggle to pick which places match the vibe of their trip. Our goal is, therefore, given a lightweight user intent input like prompts or tags and publicly available place information, produce a shortlist that is context relevant, sentiment aligned, and non-redundant, so users can move from inspiration to an actionable itinerary. Before proposing our pipeline, it is useful to recall the traditional recommender architecture used in large platforms. A common pattern is a multi-stage retrieval system. First, candidate generation retrieves a few hundred items from a huge corpus. Second, a heavier ranking model scores these candidates. And finally, a final re-ranking stage applies business rules and diversification before serving. This design works well when we have massive interaction logs, like clicks, watch time, purchases, because the models can learn fine-grained preference. However, in an early travel app like ours, three mismatches appear. First, context is underspecified, which means the same user may want quiet today and a nightlife tomorrow's kind of trip. Second, review signals can conflict, like star ratings may not match the textual sentiment. And third, top K redundancy. Highly similar places crowd the first page. This gap motivates a pipeline that relies less on historical clicks and more on semantic understanding of intent and content. To bridge those gaps, we looked at the current research landscape. We identified two main friction points in existing travel solutions: information overload and decision friction. Users are drowning in data but starving for relevant insights. Most commercial recommendation systems fall into one of three categories: role-based, content-based, and finally, behavior-based. As we established, purely behavior-based models fail for new apps without user history. Role-based systems are too rigid for the nuance of travel vibes. So, our approach leans heavily into content-based recommendation. We adopted the philosophy of the sentiment-aware multimodal topic model, or SMTM. So why this specific model? Because travel is inherently multimodal. You don't just read about a beach, you look at photos of it, and you care about how previous visitors felt about it. Standard models might look at textual keywords or visual text separately. Our approach attempts to unify these. We treat textual words from reviews, visual words from images, and sentiment signals as a combined feature set to understand the true character or by location.
So, what is the SMTM? The Sentiment-Aware Multimodal Topic Model, or SMTM, was proposed in Personalized Travel Recommendation based on Sentiment-Aware Multimodal Topic Model, published in IEEE Access 2019. The model was designed to address a key limitation of traditional travel recommendation system, which often treat textual context, visual information, and user sentiment as separate signals, resulting in an incomplete understanding of user experience. SMTM resolves this by standardizing and representing them in a unified topic space, allowing recommendations to better reflect both the content and the emotional perception of travel experiences. The model operates on multimodal data input, combining textual information from reviews, visual cues from images, and sentiment signals reflecting user emotions. From these inputs, the model jointly extracts latent topics and performs sentiment analysis, allowing each topic to be associated with a specific emotional polarity. These topics are then aligned with user sentiment and represented together with locations in a unified location topic sentiment space. Based on this unified representation, SMTM is able to personalize a top K tier list of locations, prioritizing places that match both the user's intent and emotional preference. Although SMTM is powerful in academic settings, deploying it in a real-world early-stage travel application introduced several practical challenges. The original SMTM required a very large dataset, including text description, images, label, or stably learned sentiments. This was not feasible with a new system, given the limited and uneven data. To make SMTM practical for our system, the first key adaptation is replacing the latent topics with academic-based travel tags. To design a robust and complete tax base, we base our work on two established tourism frameworks. First is the International Recommendation for Tourism Statistics, or IRTS. According to IRTS, a travel activity is not defined only by its destination, but also by multiple contextual dimensions. According to IRTS, a travel activity is not defined only by its destination, but by multiple factors. To operationalize this, we adopt the 4A framework as the structural backbone of a tag domain: attraction, accessibility, amenities, and ancillary. Each group of tags is then enriched using relevant dimensions from IRTS. For example, attraction captures core activities and purposes. Accessibility models mobility and inclusiveness. Amenities describe facilities and services, while ancillary reflects social context, time, and supplementary experience factors. SMTM also requires multimodal inference and probability distribution for each topic's sentiment, resulting in high computational costs and making it unsuitable for real-time recommendation. To address this issue, instead of performing full probabilistic topic inference, we leverage the reasoning capability of large language models. Specifically, we introduce LLM-assisted semantic tag weighting. Given only structure, location, information, and a predefined set of travel tags, the LLM assigns continuous importance weights to each tag, capturing semantic relevance without heavy probabilistic computation. This approach preserves the core idea of SMTM, semantic and sentiment-aware representation, while significantly reducing computational costs and improving scalability. In detail, for each location, we provide Gemini with structured location information together with a predefined set of travel tags. Gemini role is strictly limited to assigning relevance weights to the given tags based on how strong each tag characterizes the location. These weighted tags form a compact semantic representation. For example, highlighting whether a place is more related to beach, quietness, or crowdedness. The resulting tag weight pairs are then stored in the database and reused during recommendation, allowing us to approximate topic relevance without expensive topic inference, while remaining scalable and efficient. A common limitation in early-stage recommendation systems is that user context is often underspecified, which means user inputs are typically short and vague, such as "I want a place for deadlines alone," which makes it difficult to explicitly capture context from the prompts alone. To address this, we studied the work of Adomavicius and Tuzilin in 2011 on context-aware recommendation systems from Springer that make our systems can embed contextual dimensions directly into the text space. In addition, we use Gemini to interpret the intent and assigns relevant weights to context-related tags such as quiet, family-friendly, or evening activities. This prompt-to-tag mapping allows the system to recover implicit context, even when it is not explicitly stated by the user. As a result, the recommendation process becomes context-aware by design, without requiring additional inputs or burdening the user. Next is the confliction in review signal. Prior research by Shan et al. In 2018, inconsistent investigation between online review content and ratings in the AMCIS 2018 shows that the numerical rating and the sentiment expressed in the review text are not always consistent. For example, a review may have a high rating but contain negative sentiment, or vice versa. Relying on only one of these signals can therefore lead to misleading relevance score. To solve this problem, our system combines both user rating and textual sentiment when evaluating reviews. We use VisoBird to estimate sentiment polarity from Vietnamese review text, as it is a pre-trained language model specialized for Vietnamese social media and user-generated content, which closely match the nature of travel reviews. In our design, sentiment is treated as a secondary signal, used to refine and stabilize the rating-based score rather than replace it. This fusion allows us to reduce the impact of inconsistent reviews and obtain a more reliable representation of user perception. Another key challenge in our system is top K redundancy, where the recommendations may cluster around a narrow set of preferences. To address this, we use maximal marginal relevance algorithm for balancing diversity. First, we introduce entropy based on the user preference vector. This entropy reflects how focused or diverse the user's preferences are. A low entropy indicates a very specific intent, while a high entropy suggests broader interest. Then, we use this entropy value to dynamically adjust the parameter lambda. For users with focused preference, lambda is increased to emphasize relevance. This adaptive strategy allows us to mitigate top K redundancy in a user-aware manner rather than applying a fixed diversity constraint. This is the summarization of the end-to-end recommendation pipeline of our system, from user input to the final top 10 suggestion. The process starts from the user side, where the user provides an input in the form of a natural language prompt and selected text. This input is then transformed into a user preference vector by Gemini, which we refer to as the domain vector. On the system side, each location is already represented as a location feature vector stored in the database, constructed from weighted semantic tags. We first compute a relevance score between the user preference vector and each location vector. This score is a weighted combination of semantic similarity, measured by cosine similarity, and a review-based score, with weights of 0.7 and 0.3 respectively. In parallel, we estimate the entropy of the user preference vector to calculate the parameter lambda, which reflects how specific or diverse the user's intent is. These scorings are then passed into the maximal marginal relevance re-ranking module, or MMR, where we balance the relevance and diversity to reduce redundancy among recommended places. Finally, the system outputs the top 10 recommended locations, which are both relevant to the user's intent and diverse in experience. For the implementation and integration, implementation matters because our contribution is a working pipeline inside a product. On the client side, GoTogether collects a prompt and optional tags, then displays explanations via the selected tags. Here are the tech stack involved in our project. For a core feature implemented in our application, the recommendation system. As we mentioned, users will enter their prompt and choose preferred tags. This will be processed with the existing data and output the AI recommendation. As for the following system flow, we will present further in our demonstration video. All the travel features mentioned here will also be shown in a demo video. We evaluate the system from two angles: measurable behavior of the pipeline and subjective user perception. For this iteration, we focus on user perception through a survey of 16 participants. Results are encouraging. For intent and understanding, 56.25% rated the system as 5 out of 5 and 25% as 4 out of 5. Only 18.75% rated 3 or below. For vibe matching, 75% rated 4 or higher, and 81% reported that the top 10 list was sufficiently diverse. In terms of decision support, users considered on average about 5.3 places out of 10 as viable options, which suggests the list is selective but still offers choices. Regarding interaction design, 56% prefer combining prompts and tags, while the remainder prefer text only, indicating that the hybrid input is valuable, but we should keep a low friction option. Finally, 56% perceived the response time as fast enough, and most users reported moderate to high time saving compared to manual search. These findings validate the pipeline's direction and highlight clear next steps for performance and UX refinement. As for the key technical implementations we did, first is the practical taxonomy, which bridges tourism features frameworks and context modeling. Sentiment rating fusion model, which handles review inconsistencies in Vietnamese. Finally, entropy-guided MMR re-ranker, which improves top K diversity without sacrificing relevance. This all concludes to a deeper user insight. For our future work, we intend to implement auto-crawling data from additional sources on the internet, reinforcement learning from the behavior of users to deeper user insight, and finally, improving explanation of models result. And thank you for listening.